Log on, tune in, find out. Another good idea from Cambridge.
Our next speaker is Florent Baudier, who will speak about coarse Lipschitz embeddings of expander graphs and cotype.
Okay, thanks, Asa. So, I think first of all, we must thank the organizers and Newton Institute staff for this very nice week in Cambridge. So, thanks. All right, so today I'm going to talk about embeddings of expanders. So I'll start with a couple of definitions to fix the ideas and the notations. So that the GM BVNEM a family of connected a family of graphs of degree B bigger than 3. So this is fixed. So GN is a family of expander graphs if the following holds. So the first assertion is the cardinality of Vn tends to infinity with M, and so there exists a positive epsilon such that, so for any graph you can define the trigger constant, so which is by definition the minimum of such a ratio where Sm is a subset of the vertices whose cardinality is less than Vn over 2. And this has to be bigger than epsilon for every n. Okay. Okay, where the round of Sn is the boundary of the subset, which means it's the set of edges such that U is in Sm and V does not belong to Sm. All right. So, so of course there exist families of expanders. Pippenger in late 60s gave a proof, a probabilistic proof of that, of the existence. And I mean, the main issue was to give an explicit construction of expanders. And Margulis came up with the proof of that in 76. And it's, I mean, the proof uses deep tool or algebraic tool like cache down property T and stuff like that. So, but okay, now we are able to explicitly construct many examples of expanders. Okay, so in my talk, I'm going to focus on a particular type of embeddings, namely the coarse embeddings. And into, I will restrict myself to into Banach spaces, right? So I will say that Gn admits an equicoarse embedding into a Banach space X. So of course the definition makes sense for a family of metric spaces, and here we can take any metric space. So first thing, okay, there exist two maps, non-decreasing, and maps from Gn to X such that so rho minus of t tends to infinity with t, and the following inequalities hold. Less than fn of x less than rho plus this. Okay, where Dn is the shortest path metric. On Gn. Okay, here Gn is a family of graph. So I think the terminology equicourse is clear, because in the definition the two functions rho minus and rho plus do not depend of the metric space, right? And just to mimic the terminology with equi-uniformly continuous family of mapping. Okay. And so Gn admits an equicourse Lipschitz embedding into X if so there exist two constants such that and maps from Gn to X such that you have this. All right, and here the C and D are universal constants. Okay, of course, if okay, D has to be strictly positive. If C here, I mean, is equal to 0, you have the classical notion of Lipschitz embedding. Okay. Right. So now I give a state of the art about coarse embeddings of expanders into Banach spaces. So it's closely related to the Novikov and Bomkon conjecture. So one wants to know in which nice Banach spaces can we coarsely embed or not a family of expander graphs. Okay, and so now expanders emits an equicourse embedding So the first result is a Hilbert space. Okay, so it's also true that you cannot coarsely embed an expander into LP, let's say little p, for p between 1 and 2. Okay, so
because we're dealing with normed spaces, you don't need the C in the definition. It's equivalent. You can embed with a C and without a C.
yeah.
So it's just an unnecessary parameter in this one.
Huh?
The additive constant is not necessary for normed spaces.
Yeah, here, but okay, but I mean, for yeah, okay, it's for matrix spaces.
Yeah,
You
for
need
normed
extra-
spaces you don't need.
I mean, it's okay. So I think it's Lipschitz for large distances.
But a sequence of expanders admits an embedding Lipschitz for large distances, if and only if it admits a by Lipschitz embedding
Yeah.
into a normed space.
Okay. Yeah.
For normed spaces, this is just
Yeah.
an easy geometric fact.
Okay. Yeah. So this is Landia's Linear and Rabinovich in 95, and for p bigger than 2, okay, there is a proof of a two-check. '97. Okay. Right. Then, so here, I mean, the proofs are very similar. I mean, I mean, all the proofs to prove non-embeddability of expanders are rely on the existence of Poincare type inequality. Okay. And then there is this result of Ozawa, Takaozawa. So there is no coarse embedding of an expander into Banach space X, such that so the unit ball of X is uniformly embeddable into a Hilbert space. This is due to Zawa 2.4, and it gives you a nice class of Banach spaces such that you can not embed coarsely a family of expander graphs. So in particular, if X is super reflexive, with an unconditional basis. Okay,
Even a Banach lattice with cotype.
yeah, but okay. I don't give the full power of the result, but I get back in a minute. Just to not to confuse you, I focus on superreflexive for now.
What is the superreflexive?
Okay, so superreflexive, it's okay. If you think geometrically, it's a Banach space which admits an equivalent uniformly convex norm. Okay. So, I mean, uniformly convex means that if you take 2 points on the unit sphere far apart from a epsilon distance, then the midpoint, you can control the distance between the midpoint and the sphere with a delta of epsilon, but not which is uniform in the point. Okay. So this comes from this comes as a byproduct of the a paper of Ted Odell and Thomas Rumprecht.
Why is it in particular?
94. That paper on the distortion problem. Okay, and so even you can replace this assumption and take a superreflexive lattice.
No, with cotype. Banach lattice with cotype.
Yeah.
Not even cotype.
Yeah, I know, but okay. Right. Okay. So the next result is okay. It's still true if X is uniformly curved. Okay, so this is due to Vincent Lafort. I mean, it's written in the paper of Pizier, in the memoir of the EMS. Okay, so I won't give the definition of a uniformly curved space, right? But the thing is that uniformly curved implies uniformly convex. Okay. And the last two results I want to mention.
It's the same as superreflexive, or what's
If you're a uniformly convex, you're superreflexive. But if you're superreflexive, you can renorm your Banach space such that with the new norm it's uniformly convex. Okay. Right. So there exists a family of expanders which does not admit an equicourse embedding into any superreflexive Banach space. Okay, so here, okay, it can be proved. Okay, actually, it's into any Banach space with a non-trivial type. All right. So there is one construction due to Vincent Lafort I think it's been published in 2008. Okay, it's an algebraic construction. And there is another construction, a combinatorial one, from Normandel and a Safnauer. Okay, so combinatorial construction. So here the construction uses a strong property T, okay, stronger version of property T. And here, I mean, it's in the paper about nonlinear spectral gap using a zigzag product of graphs. And it's very, very tricky construction to prove, okay, that and it's only one family. So, these are really, really deep results, right? Okay. Okay, so now one possible conjecture is that no expander admits an equicourse embedding into a super reflexive Banach space. Okay, this is a, I mean, beautiful question, which is still open, right? But as mentioned, Asaf, in many places here we know better, all right? So, for instance, here, you can, it's true if X is a Banach space with an unconditional basis with finite cotype. Okay, and here the construction gives better into any Banach space with non-trivial type. Okay, so it means type strictly bigger than 1. Okay, and one thing here is you cannot remove this this assumption here. Okay.
What is unconditional basis?
So it means that okay, so if you have a Schauder basis, it means that the expansion is still convergent under permutation of the indices of the element of the basis, right? So even if we don't know this conjecture, there is this probably optimal conjecture into a Banach space with finite cotype. Okay, now I should probably give a definition of what is a cotype property for a Banach space.
this for cotype 2?
Sorry?
Do you even know this for cotype 2?
No. I mean, and even for a non-trivial type, I mean,
And if instead of no expander there exists a sequence of expanders,
Yeah.
they don't embed into cotype 2.
What?
We don't know that there exists a sequence of expanders that don't embed into any space with cotype 2.
Right.
It's different.
Okay. Do you think the only way to find such things is to construct expanders for the spaces?
Well, so far, yeah. So far.
okay. So, all right. So there is this big theorem of Florent Baudier, which tells you that x has trivial type if and only if x contains uniformly the L infinity ends. So I will use this notation. Okay. Okay. So here it means that there is a
For some n. For some n.
no for every end. So it means that in X you have a isomorphic copy on the L infinity end with the product measure distance, which is bounded, which does not depend on M. Okay, it contains every L infinity end.
This is different from infinity on the rest of
A theorem, but that's a theorem.
That's a theorem. Yeah. Yeah. No. Asaf gave the right definition of type. That's what I'm gonna use in the sequence. Yeah, you're right. That's a deep theorem. Okay. Okay, so what I'm going to talk now is really a small step toward a weaker conjecture where you replace equi-coarse embedding by equi-coarse Lipschitz embedding. Okay, right. And so the thing is, okay. For any expander graphs family, let's say Gn of degree B, you can slightly, okay, so what does it mean? Modify it to get a family of expanders so G and tilde of degree d plus 3 such that if g and tilde equi Coarse Lipschitz embed into x, then x contains the L infinity n. Right?
So the point is to get cotype and not superreflexive. Because for superreflexive, we know that no expander is embedded by Lipschitz or coarse Lipschitz into any superflex. Because superflexive space is a non-trivial Markov type.
Yeah.
So the issue is cotype versus superreflexive.
Yeah, here it is. Yeah.
Good question.
Okay, so there are two ingredients to prove this. I mean, it's just I mean we knew more or less all the tools already. It's just when you put the things together in the right way, then you get this result. Okay, so the first ingredient is here what I call attachment argument.
But you see, infinity has nothing to do with G and right? So X contains L infinity and somewhere else, right? So it doesn't say that it's somehow like span of the images of Gn.
Definitely.
Huh?
Definitely, yes, what you're saying.
So it's just somewhere else, though, I see.
Okay, so there is this, I mean, beautiful argument that Gideon gave us when. We proved a result with Gilles Lancien about Lipschitz embeddings of locally finite metric spaces into Banach spaces with a cotype. And Gideon gave us this argument that the converse holds. And I mean, it's really nice. So I'm going to sketch this. So you look at these graphs. Okay, so n and k are integers. And you look at the, okay, so it's the, in 2 dimensions, you look at the grids. Here. And you draw an edge between two vertices if the distance between 2 points in the L infinity distance is 1. Okay. So what you get actually is something which is really, I mean, connected. You have edges almost everywhere, right? And of course the degree here is unbounded, right? When, I mean, the degree grows up with n and k, right? So you look at this graph, and the thing is, so if you can embed it equal Lipschitz into x, then x contains the L infinity s. So, and how can you prove that? I mean, So probably for people in Banach space geometry, it's not. I mean, it's something that you've seen many times. So the thing is, you can, in a very obvious way, define a Lipschitz. Okay, so let's say equi-Lipschitz, embedding into the ultra power of X. Okay, so you take the bounded sequence of element in X, and you quotient by the subspace of. You take an ultra filter and you quotient by the subspace of the sequences that tends to 0 in norm, right? And doing that, your additive constant, you kill your additive constant, and you get a Lipschitz embedding into XU, right?
So your original ingredient was equally.
Yeah. So this is the first step, and then okay, you want to use the differentiation theory, okay? But here X is any Banach space, so you don't have it's probably not reflexive. You don't have ORNP property or stuff like that. So you cannot use the EV theorems, okay? But if you use the Weak-Star differentiability, argument, I think it's Heinrich and Mankiewicz.
So you can do that in every Banach.
Yeah.
What is this?
This you can. So you can embed. No, there is a linear embedding. A linear embedding into the double dual. Okay. And now, okay. And now it's of the L infinity ends. All right. There is a linear embedding of the L infinity ends into the double dual of your ultra power of X. Okay. And then, okay, we are left. Okay. Now you use the weakest local reflexivity principle. That's the finite dimensional subspaces of the double dual have an isomorphic copy in the Banach space. So you can go from X double star to XU double star to XU, and then I mean, it's a classical result in local theory of Banach spaces that you can pull back, okay, your finite dimensional subspace of the ultra power of X into X. So you use the classical theory, and then you can embed it into X. I mean, this argument is very nice. Okay, so this was the first step, and then so I have to tell you what I mean by slight modification. All right. Okay, so the second step is to to use a simple lemma, which is the following. So, I mean, there are many, you can play with this lemma and you have many versions of it. So I will give one, which is maybe not optimal, but I mean, it's sufficient. So, let K be a finite graph. Okay, and epsilon is a fixed positive number. Okay. So there exists an embedding from K into L, where L is a three-regular graph, such that you have this. Okay, so here the distance is in L, here the distance is in K. It's always the shortest path distance. Okay, so S and S. Okay, S is just a scaling factor. Okay, think of S as a very large. Okay. All right. So I'll skip the proof of this lemma. Okay, first thing. So the distortion of your embedding, which is this, okay, is less than 1 plus epsilon. So an epsilon is arbitrary, can be arbitrarily small, right? So let's call it expansion and contraction. Alright, so I drew a picture to show it works for a very simple graph. So let's take this graph. Okay, so it's a very simple example, so probably we can do better, but okay. Anyway, so here this vertex is of degree 4, all right? So what you do is, okay, you blow up your graph, and to each vertex, you map it. So you take a regular string of depth large enough. So large enough means that you want to have at least the number of leaves is at least the number of the maximum degree of the graph. Okay, and in such a way, to any edge here, you can assign a leaf here. Okay, so you build your graph. Okay, so I do it quickly. And so on. Okay, so here for this edge, you choose. I mean, for the, let's say this one, you choose a leaf here, and you choose a leaf in this tree here. Okay. And okay, they are adjacent, so you draw a path between the two leaves, and okay, a path of length s. Okay, and you do that. I mean, you do that for every possible edge here. So, for instance, you get this. Right. You get this. And this. And all your paths here are of length s. Okay. So now, if you compute your expansion, okay, for graphs, one only has to check on the edges. Okay, the maximum expansion is attained on edges, right? So you look at two points here that are edges.
You said 3 regular. I see many degrees.
There
See
are
many
some-
degrees, too many degrees.
Also,
Yeah.
some leaves.
You meant to say
Can
bounded.
connect them every.
At most.
You meant to say bounded degree at most 3, not 3 regular.
Oh, yeah, okay. Yeah, but I mean, you can add
You can
self-loop
add
and
some-
blah, blah, blah. But
Oh, you want to.
yeah. No, of course it's,
Okay.
yeah, at most 3, yeah. You can add self-loop and to make it regular of the grid string. Yeah, of course, yeah. So when you compute the expansion, you check on the points that were adjacent here. And here, so the distance between x and y, I mean, let's say it's 1 and 2. So, let's say the depth of the tree is r. So here it's 2. The expansion is less than s plus 2r. Okay. And the contraction. Well, you take any two vertices in this graph. Okay, there is a shortest path. You take the two images, and you go on this shortest path. Okay, and if you take another path, it's larger. So you can see that the contraction is less than 1 over epsilon. But at least you in every path, there is at least the distance between the two vertices here times s. Then there is something going on in the tree, but okay. you don't mind. So, of course, your distortion is this, and you choose S big enough to get 1 plus epsilon. All right? Because R, the parameter R is depends only of the maximum degree of your finite graph. Okay? And so now, so of course you take your family of graph R and K. You can apply to this family this trick here, this construction. So you can embed 1 plus epsilon into let's say L and K. Okay. And here, okay, the degree is at mod 3, right? So now let's, okay, there is a last step. So let's say the diameter of L and K is D and K, and the number of vertices is M and K. So, okay, one more here. So now the degree is bounded, but you really increase the number of points, right?
So it's not expander anymore.
No, but here it's only any graph. But okay, now the thing is, okay, take your favorite family of expander. Okay, you can choose you can choose n big enough such that there is a gn. So inside the gn, okay. So here it's gn of GM with n big enough. You can choose points, m and k points here, far apart from each other, where the distance is the diameter. Okay, you take m and k points, where all the distances between them is bigger than d and k. And now what you do is, okay, you take any bijection between L and K and the set of points here. And what you do is, if there is an edge between 2 points, you draw an edge here. So you redraw your family of graph here inside. For 1 L and K, you redraw L and K into G of M for M large enough. And so what you do is you add, at most 3 edges here. And the only property of and so you have an isometric copy of L and K into this, because the points are far apart for the diameter. Okay, so it doesn't interfere with the existing edges. And then the family you get is still an expander because you add only edges. Okay, and that's I mean, that's the only property that we use. So it's really weak. Okay. And okay, so it's really a small step. And now the problem is instead of doing these two steps, step by step, we can do the things simultaneously, right? But the thing is, if you take your family, you take one errand k, what you can do is you can find m large enough and not points but balls, which are far apart from each other. Because here I use 3. But actually, you can use a line or something with enough points, right? Here it was just, you can use just line with enough points. So the graphs are connected, so you can find balls with ready large enough so that you have enough points inside, which are far apart from each other. But then, if you want to apply this construction, okay, you had edges, but you had points. You had path. So it breaks the expansion property, right? So now the next step is, okay, can we can we not add path, but maybe connect the existing edges to other edges in the graph? It's something, this is something that has to be improved, right? And so here it was for coarse Lipschitz or Lipschitz embedding, but if you want for coarse embeddings, what you need is, Schichman arguments works for coarse Lipschitz, but I think we don't know if there exists a family of graphs such that if you equicoarsely embed into X, then it forces to have, let's say, L1 ends or L infinity ends. There is something that we miss too. So, yeah, I think it's enough for this week. Thank you.
Any questions?
Doesn't this answer this question that you mentioned? That
Which one?
so you found a family of expanders which doesn't embed in any space with finite cotype, is that right?
By Lipschitz, not coarse.
Okay. Sorry.
Any other questions? So, Sergey, do you still want to show? Yeah. So, Sergey Konyagin said he solved made progress on Guy Kindler's problem from 2 days ago. So he wants to quickly show us the solution, and then we'll end.